Hello, in this video we will be continuing to look at individual mechanism steps. In the last video we talked about curved arrows and how they show you the details of how electrons move within a molecule or set of molecules to make bonds, break bonds, and so on. In this video we'll be looking at how the energy changes in a mechanism step and the relationships between starting materials and products and what are called transition states. To really understand a mechanism we have to look at several different things. First of all, when a mechanism step happens, if two molecules have to come together, how do they come together to react in a particular step? So individual molecules have to come together in certain ways, and then whole groups of molecules have to come together in certain ways. So what do two species need in order to undergo a reaction step? Well, first of all, they have to collide. They have to somehow come together. They can't react with each other if they're not in the same vicinity. And they have to come together in the right orientation. In other words, they have to come together in such a way that the atoms that are actually going to react with each other are coming together. And they have to have enough kinetic energy in order to allow the reaction to occur, because every step requires an energy to actually happen. That energy is supplied by molecules bumping into each other with certain kinetic energy. And then how do their potential energies change as each step proceeds? So at one point they have a certain amount of energy. At another point they have a different amount of energy. How does that energy change as the reaction proceeds? So we'll be looking at all those factors in this video. So let's analyze the following reaction and its mechanism. It's a pretty simple reaction. It's one that we will again learn later on. Basically all it's saying is that a molecule of methanol, that's what this is, and a molecule of HBr react to produce a molecule of this compound called methyl bromide and a water molecule. So it's a pretty simple reaction. Essentially just the OH group is switching with the bromine in this reaction. And here's the mechanism. Again, it's a pretty simple mechanism. We'll just look at the details at this point. You don't have to know the mechanism. We're just using it as an example of energy. So in order to react, a methanol molecule and an HBr molecule have to bump into each other. The HBr molecule will give away an H+ and attach it onto this oxygen. And what's left over will be the Br-. So again, this is just a simple acid-base step. HBr is the acid. It's donating a proton to this oxygen. The oxygen is then picking up a positive charge and an extra hydrogen. Then, in the second step of the mechanism, that molecule that we just produced here, actually it's not a molecule, it's an ion, but this polyatomic ion with its positive charge bumps into the bromide that was left over from here. So the bromide's coming right back in again. And what's going to happen is the bromine is going to attach onto this carbon of the CH3, and this group, which you can see would become water, H2O, becomes water. So the Br- attaches and the water unattaches, and you end up with methyl bromide and water. And again, as is always true of all mechanisms, if you add this up, canceling out everything that appears on both sides, you'll end up with this overall reaction. So again, a pretty simple mechanism. So here's the first step in a mechanism. And again, we're going to analyze each step in detail, looking at the energy relationships. So what has to happen for this mechanism step to happen? Well, as I said, the methanol molecule has to collide with an HBr molecule. So I have models here. This is a methanol molecule, and you can see the carbon, 3 hydrogens, oxygen with its hydrogen, and 2 lone pairs. So this is the methanol molecule, and this is an HBr molecule. So there's a hydrogen, there's a bromine, 3 lone pairs on the bromine. So what has to happen for these two to react together? Well, first of all, they have to bump into each other. So this one's floating around in solution or in the gas phase, either one. This one's floating around in solution in the gas phase, either one. Most of the time they miss each other. Every once in a while they bump into each other. Do they react every time they bump into each other? No, absolutely not. Well, why not? First of all, they may just kind of mosey in and kind of barely bump into each other, not enough energy. But even more important, they have to collide in a particular orientation. So what has to actually happen? A lone pair on the methanol has to actually come in at exactly the right angle with a hydrogen on the HBr. In order for that hydrogen to be transferred to the lone pair, they have to bump into each other in that orientation. Well, that's pretty rare. So certainly if they bump into each other this way, no matter how much energy, it's not going to work. Or if they bump into each other this way, no matter how much energy, it's not going to work. They have to bump into each other in exactly the right orientation. So, as indicated here, you'll notice that the lone pair of electrons on the oxygen gets donated in here to form an OH bond. That pair between the hydrogen and the bromine goes off onto the bromine. So I've showed the curved arrows here in the formalism that we learned in the last video. And so, of course, the oxygen becomes positive, has an extra hydrogen, and the bromine goes off by itself as Br minus. But again, the hydrogen and the oxygen have to be in the right orientation for that to happen. Now, there's another reason. Even if they do bump into each other in the right orientation, if they just barely bump, it's not going to work. There has to be a certain amount of energy with which they bump into each other in order to transfer that hydrogen onto the oxygen. In other words, this is the energy of the starting materials, the methanol and the HBr, and this is the energy of the products. Well, products are the first step. We're not to the second step yet, but products are the first step, which is the protonated methanol and the Br minus. This conglomeration of atoms certainly has more energy than this conglomeration of atoms, but there's also a hill in between, and it's true that every mechanism step will have a hill in between. That's because it takes more energy to actually begin to break the bonds than you will ultimately get at the end. So here's the starting materials. Here's the product. Halfway in between, that hydrogen is partly bonded to the oxygen and partly bonded to the bromine, and that situation where it's not completely formed a bond yet, not completely broken a bond yet, is higher energy than either the one where the hydrogen's attached to the oxygen or the one where the hydrogen's attached to the bromine. So there's a little bit of higher energy in between there, so there's a hill in that particular mechanism step and in every mechanism step. Like every mechanism step, like every reaction, it will have a delta H. So the delta H, the difference between the energy of the starting and the product of that mechanism step, is some particular value represented by this double-headed arrow here. And every step will have an energy between the starting material and the top of the hill. That's sometimes called the activation energy for that particular step. In other words, that's the amount of energy you have to put into it before it can go back down again to the products of that first step. Why? Again, well, I've sort of hinted at it. We'll see again a little bit more in a minute. Let's look at the second step. Since this mechanism has two steps, it has two delta H's, one for the first step and one for the second step. Two energy barriers in between. So here's the second step. That protonated methanol that we just made in the first step reacts with the bromine. Actually, what happens is the bromine comes in from the back of this molecule and pushes out the water from the front of the molecule. And so these molecules together have some amount of energy represented by this line right here. These molecules have much lower energy now because now we're gone back to stability. This is an actual molecule, and this is an actual molecule. And so it's a much lower energy, so the delta H for that first step would be negative. If we go back and look at the previous step, the delta H for that first step is positive. You have to put energy into it total, not even including the energy you have to put in to get to the hill in between. But the second step, there's a negative delta H because you're going from this set of molecules to the final product. So it's downhill by a particular amount. Then there's also an activation energy for this step to go from the intermediate up to the top of the hill and then back down again to the final product. Again, why is that hill there? Well, we'll talk about it in a minute. But as indicated over here, the ones formed in the first step, the CH3OH2, has to collide with the bromide. So again, here is my bromide molecule. It's just a bromine with 4 pairs of electrons. Here is my protonated alcohol molecule, C2 oxygens on that oxygen. In order for the bromide to push out that water molecule, it actually has to come in on the back of that molecule, so it has to collide in that particular orientation, at which point then the water group will leave from the other side and these 3 hydrogens will switch over. But the point is it has to collide in that particular orientation and with enough energy for it to actually get in there, form a bond, and push out that other bond from the other side. So here's the mechanism together. First step, second step. Here's the total energy diagram. So there's that first hill you have to go over to get to the intermediate. Then the second hill you have to go over to get to the final product. Turns out in this case the second hill is higher than the first hill. It's not always going to be true. Sometimes the first hill is higher. In this case the second one is higher. And by the way, there's 2 hills here because there's 2 steps in the mechanism. If there were 3 steps in the mechanism, there would be 3 hills. If this was a one-step mechanism, as we've seen can happen, then of course you just have 1 hill you have to go over to get to the final product. But here's some terminology for you. The energy difference between the starting point and the top of the highest hill, in this case the second one, that's called the activation energy for the whole reaction. It's how much energy you have to put in to make the reaction happen in order to get to the final product over here, even though the final product is lower in energy. And then this is what's called a transition state for the first step. This is the transition state for the second step. This is the activation energy, and this of course is the delta H for the overall reaction from there to there. Again, why is there a hill for each step? Because halfway through a step happening, there are incomplete bonds. You haven't completely broken any bonds that are going to be broken. You haven't completely formed any bonds that are going to be formed. And sometimes both happen. Bonds are breaking and being formed at the same time. And so there's a higher energy. That's a higher energy situation than having complete bonds. So the highest energy state, where the bonds are the least complete, that's what's called the transition state, as I've said. So here's that. Our first step in the mechanism, there's the transition state for it. There's the energy of the starting materials. This is the energy of the intermediate. Can we draw what it would look like at the transition state? Yes, we can. So again, here is the overall reaction. Here is the first step showing the curved arrows. And then what we notice is that halfway through, in other words, the top of the highest hill, we have this conglomeration of atoms. So how do we draw that thing? How do we guess what that is? We'll notice that down here, we're forming an oxygen-hydrogen bond that's not there to begin with, but is there at the end. That's halfway formed in the transition state, so we put a dotted line in there to represent the hydrogen that's not yet completely attached to the oxygen, but is on its way to being completely attached to the oxygen. And furthermore, notice that there's an HBr bond that's breaking, so the bond between the hydrogen and the bromine is there at the beginning, it's not there at the end, so it's halfway there in the transition state. So this hydrogen, you can almost squint at it and imagine it was attached to the bromine, it's being transferred over onto the oxygen. You can just sort of imagine that hydrogen moving from being attached to the hydrogen to being attached to the oxygen. Furthermore, the oxygen was neutral to begin with, and it's positive at the end of that step, so it's partially positive in the transition state. And the bromine was neutral to begin with, it's negative at the end of the process, so it's partially negative. This little symbol is a delta, it means partial, just like in calculus partial derivatives. So it's partially negative and partially positive in the transition state. And the square bracket is to indicate that this whole conglomeration of atoms is the transition state. And this is what it would look like if you could see it at the point where its energy is the most, right here. So then these arrows are to show that this stuff goes to the transition state, which then goes to this stuff over here. If you're asked to draw a transition state, first draw the molecules as good Lewis dot structures with atoms close to each other that are actually going to become bonded to each other. Put in the curved arrows, and then look for bonds that have changed. Say there's a bond in this in the starting material but not in the product, then it's half of a bond in the transition state, or a dotted line. Now, you try drawing the transition state for this second step. So notice again that the bromine with its negative charge is coming in from the back of the CH3 group, and it is becoming attached to the CH3 group. The bond between the oxygen and the CH3 group in the starting material is breaking, and the water is going off by itself. So again, in this space right here, or on your paper obviously, draw the conglomeration of atoms with partial bonds represented by dotted lines, partial charges represented by delta positive or delta negative, that would exist at the top of this hill right here, in other words at the transition state. And we will talk more about that in class. Thank you.